For more than 2 centuries, Isaac Newton's law of universal gravitation reigned almost unchallenged. Published in 1687, it held that any two masses attract one another with a force that grows with their masses and falls off as the square of the distance between them, and it was a triumph of astonishing scope, explaining the fall of an apple, the orbit of the moon, the tides, and the motion of the planets, and predicting in its greatest coup the existence and very position of Neptune. Yet by the early 20th century 2 deep problems had accumulated. The first was small and specific, the orbit of Mercury. Its point of closest approach to the Sun slowly rotates, and after every known planetary tug had been accounted for, a stubborn residual remained, an unexplained drift of about 43 arcseconds per century that no amount of Newtonian bookkeeping could remove. The second problem was conceptual and far more sweeping. Newton's gravity is an instantaneous action at a distance. Move a mass here, and its pull everywhere else updates at once with no delay. But Einstein's own special theory of relativity had just established that no influence can travel faster than light, welding space and time into a single 4-dimensional spacetime, and abolishing the very notion of a universal instant. A gravity worthy of that new picture could not be a theory of instantaneous forces, it had to be a field theory in which gravity propagates at finite speed. Einstein wrestled with the problem from 1907 to 1915, guided by a single insight about falling bodies that he called the happiest thought of his life, and the culmination was a set of field equations he presented in Berlin in November 1915. Their very first success was to compute Mercury's stubborn drift and obtain exactly 43 arcseconds per century, with not a single free parameter to adjust. That happiest thought was the equivalence principle, and its root is a coincidence so exact it demands explanation. There are, in principle, 2 quite different kinds of mass. One is inertial mass, a body's resistance to being accelerated. The other is gravitational mass, the charge that couples a body to gravity. Nothing in Newton's scheme requires them to be equal, yet they are exactly, and this is why every object falls with the same acceleration regardless of its weight or composition, as Galileo argued and as an astronaut dramatized on the Moon in 1971 by dropping a hammer and a feather together, watching them strike the dust as one. This equality has been tested to staggering precision. A satellite mission called Microscope, reporting its final results in 2022, compared the fall of platinum and titanium masses in Earth orbit, and found them identical to about 1 part in 1,000 trillion, the most stringent such test ever made. Einstein's leap was to raise this coincidence to a principle. Imagine a sealed laboratory. If it rests on the Earth, objects fall to the floor. If instead it is far out in space, accelerating under rocket thrust, objects fall to the floor in exactly the same way. The equivalence principle asserts that no experiment inside can tell these 2 cases apart. Gravity is locally indistinguishable from acceleration, and its mirror image is just as striking. A laboratory in free fall, an elevator whose cable has snapped, or a spacecraft in orbit, is indistinguishable from one drifting in empty space, for inside it gravity has vanished and everything floats. This is exactly the weightlessness of astronauts, who are not beyond gravity at all, for the Earth's pull at the space station is nearly its full surface strength, but are simply in perpetual free fall. Gravity, alone among the forces, can be made to disappear at any point merely by falling with it, but only at a point. The word local is essential, because the cancellation is never quite perfect over any real extent. A true gravitational field like the Earth's is not uniform. It points toward the planet's center and weakens with height. 2 apples released side by side in a falling elevator drift slowly toward each other, because each falls along a line aimed at the same center. 2 apples one above the other drift apart because the lower falls a little faster. These residual relative accelerations are the tidal forces, and they are the true, unremovable signature of gravity. No choice of falling frame can transform them away, and they are, as we shall see, the physical face of something deeper, the curvature of spacetime itself. To make that idea precise, we need geometry. Special relativity describes a flat spacetime in which the interval between 2 nearby events, a kind of 4-dimensional distance blending time and space, is fixed and the same for all observers. General relativity's central move is to let that geometry curve and to let the recipe for the interval vary from place to place. The object that encodes this is the metric, a set of 10 functions of position that together specify all distances, all durations, all angles, and the entire causal structure of spacetime. The analogy that makes it concrete is a curved surface. On a flat sheet, the shortest path between 2 points is a straight line, and a triangle's angles sum to 180 degrees. On the surface of a sphere, the shortest paths are great circles, and a triangle's angles sum to more. Crucially, this curvature is intrinsic. A flat being confined to the surface could detect it by measuring triangles without ever leaving the surface, and it was exactly this mathematics of intrinsic curvature, developed by Gauss and Riemann, that Einstein needed. How then do things move through a curved spacetime? The answer is the geodesic principle. A body falling freely, feeling no force but gravity, follows a geodesic, the curved spacetime version of a straight line, the straightest path available between two events, and this quietly transforms the meaning of gravity. In Newton's picture, a planet is pulled off a straight path by the sun's force. In Einstein's picture, the planet feels no force at all. It simply coasts along the straightest possible path through a spacetime that the sun's mass has curved. John Wheeler distilled the whole theory into a single sentence: spacetime tells matter how to move, and matter tells spacetime how to curve. The geodesic principle is the first half of that sentence, and it contains the equivalence principle for free, because a geodesic depends only on the geometry and the starting position and velocity, never on the mass or make of the falling body, so all bodies must fall alike. The second half of Wheeler's sentence is the Einstein field equations, presented in their final form in November 1915, and they are the dynamical heart of the theory. Written compactly, they fit on a single line, but that line is in truth a system of 10 coupled nonlinear equations. On one side sits the geometry, a particular measure of the curvature of spacetime, the piece that cannot be transformed away by falling, and that is the mathematical embodiment of those tidal forces. On the other side sits the matter, captured by a quantity that encodes the density and flow of energy and momentum at every point. The equation says, simply, that matter and energy on the right tell spacetime how to curve on the left. A profound novelty, absent from Newton, is that every form of energy gravitates, not only mass but pressure and radiation, and even the energy of the gravitational field itself, which is why pressure adds to the crushing weight inside a collapsing star. Two features of the equations deserve emphasis. First, the constant that couples matter to curvature involves the speed of light raised to the fourth power, an enormous number, which makes gravity by far the feeblest of the forces. It takes a colossal concentration of energy to warp spacetime measurably at all. And second, the requirement that the whole edifice reduce to Newton's familiar law in the limit of weak fields and slow motions fixes that constant uniquely, with nothing left free to tune. In 1917, Einstein added one extra term, a cosmological constant, at first to allow a static universe. He later called it his blunder, yet it has returned in modern cosmology as the leading description of the universe's accelerating expansion, and whether it is truly a constant of nature remains one of the deepest open questions in the subject. Because the equations are nonlinear, since gravity itself carries energy and so gravitates, exact solutions are rare and precious. The very first was found by Karl Schwarzschild within weeks of Einstein's publication, while he was serving on the Russian front in the First World War, from which he would not return. It describes the spacetime outside any static spherical mass, a star or a planet or a black hole, and because the sun and planets are very nearly such spheres, this one solution underlies almost every classic test of the theory in the solar system. Its key ingredient is a factor that depends on a special length called the Schwarzschild radius, and that factor carries a startling physical meaning. That meaning is the slowing of time. A clock at rest deep in a gravitational well close to a mass ticks more slowly than a clock higher up, and the effect grows without limit as one approaches the Schwarzschild radius. For an ordinary body, that radius lies harmlessly deep inside it. The sun's is about 3 kilometers, buried within its vast bulk, and the Earth's is a mere 9 millimeters. But compress an object within its own Schwarzschild radius, and that surface becomes an event horizon, a one-way membrane, and the object is a black hole, a story told fully in its own chapter. Here, the same slowing of clocks that would become infinite at a horizon is, near the Earth, almost imperceptibly small. Almost but not quite, and modern technology has made it matter. The global positioning system carries atomic clocks on satellites 20,000 kilometers up, where gravity is weaker, so those clocks run fast by about 45 microseconds a day from gravitational time dilation. Their orbital speed, by the separate effect of special relativity, makes them slow by about 7, and the net correction of some 38 microseconds a day must be built into the system. Were it neglected, the navigation errors would pile up at roughly 10 kilometers per day, and the system would be useless within minutes. Every time a phone finds its position, it is quietly confirming Einstein twice over. Einstein himself named 3 classic tests by which his theory could be judged, and all 3 are now confirmed with precision. The first was Mercury's slowly turning orbit, and it carried special weight because it explained a known anomaly rather than merely predicting a new one. The theory's small correction to the Newtonian orbit makes the ellipse precess by exactly the 43 arcseconds per century that had defied every earlier explanation, a figure now confirmed to better than a part in 1,000. The second test made Einstein a household name. His theory predicts that a ray of starlight grazing the edge of the sun is bent by about 1 3/4 arcseconds, precisely twice the deflection one would guess by treating light as a Newtonian particle, the factor of 2 arising because both the warping of time and the warping of space contribute equally. In May 1919, an expedition led by Arthur Eddington photographed stars near the eclipsed sun and measured their tiny displacement, and the result, clearly favoring Einstein's value over the half-as-large Newtonian one, was announced to worldwide acclaim that November, making Einstein an international celebrity overnight. The prediction has since been confirmed by radio astronomy, tracking distant quasars as the sun drifts past them, to about 1 part in 10,000. The third classic test follows directly from the slowing of clocks. Light climbing out of a gravitational well loses energy and is stretched to redder wavelengths, the gravitational redshift. The landmark laboratory demonstration was carried out by Robert Pound and Rebka at Harvard in 1959, who sent gamma rays up and down a 22-meter tower and, using an exquisitely sharp nuclear resonance, detected a frequency shift of only a few parts in 1,000 trillion, exactly as predicted. It was a feat of precision that helped inaugurate the modern era of testing general relativity, and the same redshift is, once again, a routine correction inside the GPS. Beyond the original 3, a fourth classic test and a battery of modern experiments have probed the theory ever more finely, organized by a bookkeeping scheme in which each departure from Newton is tagged with a parameter, and general relativity makes the sharp prediction that 2 key parameters equal exactly 1. The fourth test is the Shapiro delay. A radar signal passing close to the sun is slowed, relative to its flat space travel time, because it must cross the warped spacetime near the sun. The most precise measurement tracked radio links to the Cassini spacecraft on its way to Saturn in 2003, confirming the theory to about 2 parts in 100,000, one of the most stringent solar system tests ever made. Stranger still is frame dragging, the prediction that a rotating mass drags spacetime around with it, an effect with no Newtonian counterpart at all and near the Earth, fantastically small. To measure it, the mission gravity probe B flew 4 of the most perfect spheres ever made as gyroscopes in orbit for over a year, watching for a minute twist in their spin axes, and after painstaking analysis it confirmed both the larger geodetic precession and the tiny frame-dragging effect, each in agreement with Einstein. The most spectacular confirmations, though, come from regimes Einstein never dreamed of testing. A pair of neutron stars discovered in 1974, the Hull-Staler binary, spiral slowly together as they radiate energy, and the measured shrinkage of their orbit matched the prediction for gravitational wave emission to a fraction of a %, the first evidence that such waves exist. And in September 2015, the LIGO observatories caught the waves directly from 2 black holes merging over 1 billion light-years away, the ripples matching the theory's predictions in the violent, strong field regime where its nonlinearity truly bites. The bending of light, demonstrated for a single star in 1919, becomes a powerful tool when the deflecting mass is an entire galaxy or cluster of galaxies. This is gravitational lensing, the warping, magnifying, and multiplying of the images of distant objects by intervening mass. Einstein worked out the geometry and even the perfect ring that would form under exact alignment, though he thought it too small ever to see. Fritz Zwicky pointed out that galaxies, being vastly more massive, would produce it observably, and in 1979 the first example was found, a single quasar split into twin images by a foreground galaxy, confirming the idea 4 decades on. The natural scale of the effect is the Einstein radius, set by the lens mass and the geometry of the alignment. Lensing comes in three strengths. Strong lensing behind the most massive galaxies and clusters splits sources into multiple images, dramatic arcs or complete rings, and lets astronomers weigh the lens precisely and even through the time delays between images, measure the expansion rate of the universe. Weak lensing is subtler. The deflection is too slight to make multiple images, but coherently distorts the shapes of countless background galaxies by about 1%, a signal teased out statistically by averaging the faint alignment of thousands of them. And microlensing occurs when a single foreground star drifts across a background one, briefly brightening it, a transient now used to discover distant planets. Lensing's greatest prize has been the mapping of matter that gives off no light. Because gravity bends light in proportion to all mass, luminous or dark, a lensing map is a direct map of the total gravitating matter. The most celebrated case is the Bullet cluster, two clusters of galaxies caught in collision. X-ray telescopes show the ordinary hot gas slowed and pooled in the middle, while the lensing map shows the bulk of the mass, having sailed straight through and separated cleanly from that gas, tracking instead the nearly collisionless galaxies, and with them, the dark matter. That visible offset between where the mass is and where the ordinary matter is stands as some of the most direct evidence we have that most of the matter in the universe is dark and unlike anything in the periodic table. And great surveys now underway aim to map that dark matter across cosmic time. A century after Einstein wrote it down, general relativity stands among the most thoroughly tested theories in all of science, having passed every challenge from tabletop experiments to the collision of black holes, and it is far more than a correction to Newton. It is a wholesale reconception in which gravity is geometry, time is woven into the dynamical fabric of the cosmos, and the universe as a whole obeys the same equations that bend a beam of starlight. Black holes that Einstein doubted could form are now imaged directly. Gravitational waves he wavered about for decades are detected several times a week, and the expansion of the universe itself is read off from solving his equations for the cosmos entire. And yet it is almost certainly not the last word, and it is worth being candid about the frontier. The deepest trouble is that general relativity, a smooth and classical theory of continuous spacetime, is fundamentally at odds with quantum mechanics, the equally well-tested framework of everything else, and the two give contradictory accounts exactly where both must matter: at the singularity, inside a black hole, and at the first instant of the Big Bang, where curvature grows so violent that spacetime itself should behave quantum mechanically. A theory of quantum gravity that reconciles them is the great unsolved problem of fundamental physics, and while frameworks like string theory and loop quantum gravity are pursued, none has been confirmed, and this remains frankly speculative ground. There are empirical puzzles too, which point not to the theory's failure, but to physics not yet understood. The dark matter revealed by lensing and by the spin of galaxies has never been identified as a particle. The accelerating expansion of the universe, described by that returned cosmological constant, may be a true constant, a changing field, or a hint that gravity itself behaves differently on the largest scales, and no one yet knows which. And a persistent disagreement over the exact rate of cosmic expansion, the so-called Hubble tension, may be a measurement problem or may herald new physics. These are live debates, not settled conclusions, but what is not in doubt is the structure this chapter has built: the equivalence principle, verified to a part in 1,000 trillion, the vision of gravity as the curvature of a living spacetime, the field equations that bind that curvature to matter, and the long roll of confirmed predictions, from Mercury's drift to colliding black holes. Together, they form one of the supreme achievements of the human mind, and the indispensable language in which the rest of modern astronomy is written.